Chapter 4, Lecture 4 is going to deal with the cycles, including water cycle, nitrogen cycle, phosphorus cycle, etc., carbon cycle also, which tends to be on the little tougher side, but let's start out with an easy one, the water cycle, which you probably started learning about back in kindergarten. Anyway, think of the water cycle as obviously very critical to us. We need water. We're 70% water. Our Earth is over 70% water. Also, it really drives a lot of the other cycles. Water molecule does a great job allowing other things to hang on to it. So it's kind of important in all these steps. If you take a look kind of at the right here, you can actually see, for example, evaporation from the ocean. That is driven from the sunlight. So if we didn't have the sun and the heat, obviously things like evaporation would not occur. So the sun's rays obviously come down, hit that water, and voila, we get evaporation up into the atmosphere. And of course that falls down in many different forms of precipitation, being rain or sleet or snow or even fog, which, by the way, fog is kind of just clouds that are really low, can cause it too. And of course we get dew when we get warm ground, for example, and cool air, or the opposite, we get dew forming like on our grass. That's all part of this. And a big part of this is when it leaks into our groundwater system. And of course, like in Brookfield, that's where we get, well, depending on what side of Brookfield you live on, that's where you get a lot of your drinking water from. The side the school is on of Brookfield actually gets its water from Lake Michigan. But this is a real important thing to understand, this water cycle, because it really drives everything else. And unfortunately, as humans, we kind of affect it a little bit. Good. We'll talk about that in a little bit. As I mentioned, it's powered by the sun and gravity. Gravity, because what happens is after the sun evaporates it, the gravity pulls it back down into the earth. This actually drives our winds, by the way, too. Air masses are going to carry that water vapor. Think about in the great state of Wisconsin, what happens is our wind patterns tend to be from the west to the east. So what is happening in Madison, for example, or in the Iowa, will tend to happen in Brookfield as the winds travel in that northeasterly pattern. We get evaporation. Transpiration might be a new word for you. Transpiration is real critical. That's actually water loss by plants. Water returns, of course, as I said, with rain, snow, other forms. It goes through organisms as part of its cycle into the bodies of water and evaporates again. Any large body of water, even lakes around our area and everything, have very high evaporation rates, of course, in the summertime when it's real intense sun. The groundwater actually tends to be very clean. Ground tends to purify and redistribute water very well. Not perfectly, but if it is contaminated, once it goes through the ground, it tends to clean it very well, and then we drink it, of course, but it still needs to be cleaned out with bacteria and protists and things like that before we can have clean drinking water. Surface runoff, obviously, like rivers and streams, and when it rains out, any little patterns that get created from the water, they can cause soil erosion, so that's a huge issue. We'll talk about that later when we deforest or take away vegetation. Soil erosion can really become prominent. It is the primary sculptor of landscape. Remember that for down the road when we talk about the different forms of erosion. Water is by far the most powerful, and as I said, it's a major form of transporting nutrients. Think about a river. The maybe Mississippi River, for example, that starts up in Minnesota. By the time it reaches the Gulf of Mexico, it carries a huge amounts of minerals and nutrients with it. How have we altered this? We withdraw lots of groundwater. We'll do a case study down the road where we talk about the Ogallala Aquifer, which is basically from North Dakota down to Texas, and we're withdrawing that aquifer much quicker than we really should. We're clearing vegetation, reducing filtering, we're increasing runoff. We're adding nutrients that modify the quality of the water. It pollutes it. Obviously, farming is very critical to our region and to our world, but what happens is when we add both fertilizers and pesticides to the plants, it eventually will get into the groundwater, and of course that affects us. And what's happening is we know that evaporation rates and really ultimately the hydrologic cycle is being increased quite a bit due to global warming, a topic we'll talk about in depth. It could change global precipitation patterns throughout. The next one is the carbon cycle. If you remember basic chemistry, organic chemistry is the study of carbon. We are basically anything living on this planet is carbon based. What happens is obviously when we eat plants, we get that carbon, it stays in us, and then of course when any organism dies for that matter, what happens is that's returned back to the earth. Take a look at, if you look at the diagram, the bicarbonate and carbonate dissolved in ocean water. The oceans are a huge storehouse of carbon, and what they do is when it dissolves, that should be carbonate. What happens is water stores it as bicarbonate ions. A huge concern right now is that the oceans are getting too full of carbon because of increased carbon dioxide production into the atmosphere. So we don't know what's going to happen with that. Again, a topic we'll talk about when we get global warming. Just another area right here, most of the carbon is captured in the terrestrial regions, which is the land regions. We do have a lot of carbon in the atmosphere in the form of CO2, obviously. We have it dissolved in water. We have it as a large part of our food webs, and of course the fossil fuels. If you think about fossil fuels like carbon-based coal and oil, what happens is it's taken millions and millions of years for those decaying plants and animals to form that. And what's happening now is as we burn it, it kind of prematurely releases that carbon into the atmosphere, and obviously huge problems. So the carbon cycle, there's really two key components to the carbon cycle. One of them is photosynthesis, which is when plants take in CO2 and obviously, as we talked before, create oxygen and glucose, which we like. And respiration, which is when plants and animals give off CO2, so we use that glucose and oxygen, and a natural byproduct is CO2. So it's kind of a win-win situation. We kind of take some stuff from photosynthesizing organisms and we give back that carbon dioxide so they can do that. When plants and animals die, of course, this carbon is released into the atmosphere. Over time, particularly in swampy regions, carbon can become coal, oil. Two largest reserves of carbon, very important to know, is both the land and really particularly the ocean bottom. CO2 does regulate temperature. We know that. Obviously global warming is a huge controversial issue. Scientifically, though, we know that carbon dioxide will hold heat longer. Big issue too is deforestation. When we clear trees, we burn fossil fuels, obviously. It prematurely, as I mentioned before, releases that carbon into the atmosphere, and of course we get a warm climate. The nitrogen cycle is the next one. This tends to be a toughie. Nitrogen is very important for plants to grow. Plants will not get real green without it. What it does is it actually does a great job promoting chlorophyll production, which chlorophyll, of course, is what is required for photosynthesis to occur. So what happens with this, and we're going to go through the different steps. There's about 5 different steps to this. But the long story short is that we need to get that nitrogen from the air. Remember, 78% of the air around us is nitrogen. We need to get it into the ground, into plants, and then we need to ingest plants in order to get that nitrogen in our system. Remember, we need nitrogen just as much as we need carbon. If you think about like our DNA, which is based on all those A, T, C's, and G's, we need that nitrogen in order to form our nitrogen bases, that adenine, thymine, guanine, and cytosine. So let's get this. A couple key elements that you really should know when we're dealing with the nitrogen cycle. N2 is, of course, the diatomic form of nitrogen, which is in the atmosphere around us. NO, which is nitric oxide. That's an ozone depleter. We'll talk about that big time at the end of this class with pollutants. N2O, which is nitrous oxide, also known as laughing gas. NO2, nitrogen dioxide, which is a poison. HNO3 is associated with acid rain. It's nitric acid. NH3 is ammonia. We're going to hit that in the cycle in a second. It's actually an irritant. NO2 nitrite, NO3 nitrate. Plants want nitrate, and that's its most usable form. HCO3, as I said before, is bicarbonate ions. Bicarbonate ions are those that are stored in the oceans. CO3 with a -2 charge is carbonate ions, and H2S, which is something swamps tend to form, is hydrogen sulfide. So just a couple key elements to familiarize yourself with. So as I said, the nitrogen cycle, 78% of the air around us is nitrogen, 21% oxygen. Plants need it. We need it. Best source is nitrate. That's the most usable form by plants in particular. It must be converted to either ammonia or then nitrate before plants can. So here are the steps. The first step is nitrogen fixation. So If you can imagine, in the atmosphere around us, we've got atmospheric N2. That can be fixed, if you will, in two ways. In other words, it can be captured and put into the ground. One way is actually by lightning. You may notice after a thunderstorm around here, your grass tends to get real green. It's because that nitrogen has gone through fixation. Or there's a particular type of soil bacteria called rhizobium that can convert that N2 into ammonia. The rhizobium bacteria tends to hang out in plants that are legumes, things like beans and peanuts and things of that nature. So that's the first step. We need to get that usable form of gas into the ground. Then what happens is there's another type of soil bacteria that takes over. And what it does is it converts that ammonia into the nitrate ions, which is NO3. The third step is assimilation. Think of it this way: if you assimilate information, you are learning information or you are taking it in. Plants absorb that ammonia and ammonia ions, also the nitrate ions, which is the best, through its roots. So what we're doing is we took that nitrogen gas out of the air, we went through nitrification, which is when we convert it into usable forms, either ammonia or nitrate. Now we need to get it into the plants. So this is where the plants absorb it, through their roots. Heterotrophs, by the way, eat those plants that get nitrogen, as I said before. The next way that this can actually occur is not with lightning, not with solely the bacteria, but something called ammonification, and that's when decomposing bacteria can convert dead organisms to ammonia or ammonium that can be reused by plants. So an animal dies out in a field, decomposition occurs, the fungi and the bacteria will come along, and a very particular type of bacteria will actually cause those dead organisms to break down and pull out those nitrates or nitrogen in order for plants to use it. So that's just another way that can occur. Once the plant's done and has used this and it starts decomposing, what happens is another type of bacteria, which is anaerobic, comes along and it converts that ammonia to nitrate and then back to nitrogen, and it's released into the atmosphere. What happens is it completes a cycle. So we started out with nitrogen in the atmosphere, and of course now we're returning it back to them. This is, I know, a handful. Obviously this nitrogen cycle, we'll definitely review this and do some activities in class to set. How have humans influenced it? Very important part. Well, we burn fuel, obviously, in cars. The fuel that we burn has a large amount of nitrates in it. What happens is nitric oxide can actually form and go into the atmosphere, and that can lead to acid rain. Also, we add N2O from livestock waste as a fertilizer, and that can deplete the ozone too. So livestock waste, which is commonly used as a fertilizer, farmers spread it in their fields around here, and what happens is that can actually deplete the ozone. Again, something we'll hit when we do the global warming again. Deforestation, we're cutting down these trees. Trees are loaded with nitrogen that's prematurely releasing into an environment. We add a phenomenal amount of nitrates into our crops, and that can actually cause something called eutrophication. If you think about Pewaukee Lake, which is a very nice lake, but it tends to get very full of weeds when it gets nice out. The reason that is because, and there's a series of steps we'll go through down the road, but what happens is all the farmers in this region put nitrogen or nitrates down in their crops in order for them to grow really well. Well, a lot of that seeps into Pewaukee Lake and causes something called eutrophication, which are algal blooms. And of course, we remove nitrates from the ground actually in order to use on crops, which is again prematurely using them and not part of a natural cycle. Here's just another way of looking at the nitrogen cycle. Of course, we start with nitrogen in the atmosphere, and then what happens is we go this way. We have nitrogen fixation. Nitrification is when we convert that usable form of nitrogen into a usable form for plants, which is which is nitrate, ideally. Then what happens is once we get it into the soil, we need to assimilate it into plants. Assimilate, remember, means you take in, so the plant takes the nitrates ideally into the plant. Then ammonification is another way this can run. What happens is when plants or animals die, of course, due to natural decomposition, this can get into the ground with another specialized bacteria. And once this process is all done, we have something called denitrification. And denitrification is a bacteria that is going to convert that nitrate particularly back into usable nitrogen gas that gets into our atmosphere. So it's a complete cycle. The next one, which is This diagram actually is going to show the phosphorus cycle. Phosphorus is something that we use as a fertilizer big time. Nitrogen really promotes chlorophyll production, whereas phosphates really help plants grow really big and mature. We use phosphates big time in plants. Again, if we overuse it, it's a huge source of eutrophication. The phosphate cycle is known as a sedimentary cycle because it's generally stuck in rock or the land, and it's a very slow moving cycle. We are lucky in the state of Wisconsin to have very high phosphate levels. We don't need to add phosphates to our lawns to have them look nice. As a matter of fact, it's recently been banned. We can't buy fertilizer with phosphates in it, but farmers can still put it on. Something called guano, that's bat poop. Bat poop is actually a phenomenal source of fertilizer or phosphates. It's excellent if we could ever capture a large enough amount of bat poop. It actually would be an excellent fertilizer for all our farms around here. So let's get into these here. Is actually phosphorus, of course, what it does is it's very slow moving through the cycle. As I mentioned, it is a sedimentary process, so it's found in the soil and rocks, and it's released through weathering. So chemical weathering, physical weathering, as I mentioned before, even water when it's causing erosion, this will release it from the environment. It does end up in the oceans, unfortunately, and increases plant growth, and it can limit some growth of producers too, where if we don't have enough phosphates too, producers cannot flourish. I've actually seen examples of this off the coast of Florida, where they have these huge algal blooms where they have all these phosphates from the land being released prematurely into the oceans, and we have just this huge algal bloom out in the ocean. The phosphorus cycle, then, how do we interfere with it? Well, we tend to mine this phosphate rock for fertilizers. Detergents, any detergents like dishwashing detergents tend to be loaded with phosphates. And if those phosphates get into our environment, obviously it's going to cause premature plant growth. We're cutting down tropical forests, obviously it's deforestation, which reduces phosphorus in the soil. So the soil, of course, in the tropics doesn't have very good nutrients in the first place, and this really reduces it. Human sewage and animal waste, as I said, guano particularly, which is bat poop, tends to get into the water. In the United States, of course, we've got a very good sanitation system, but other nations around the Mediterranean region, for example, human sewage tends to get into the water sources as a direct result of improper sanitation, and of course that's causing eutrophication greatly. The last one is actually the sulfur cycle, and the biggie of the sulfur cycle, you've probably all smelt sulfur before. It's kind of a yellow powder in its pure form. If you've smelled rotten eggs, that's generally sulfuric acid. When the big things with sulfur getting into our atmosphere is generally associated with acid rain. It can be a global agent also. But we need it in our body systems too. So this is yet another one where we need to eat plants or something that ate plants and get these into our system to make up our proteins and all those essential vitamins that we need. Plants absorb this through their roots. Of course, we can eat the plants to get it. Sulfur tends to be tied up in the rocks, just like phosphorus. It's deep in the oceans, the hydrothermal vents particularly. We do find a very trace amount in the atmosphere. This is released from volcanoes. A lot of times people think others die in volcanoes from the ash and things like that. It tends to be from the gases that are released, particularly things like sulfur. In swamps, we have anaerobic bacteria working to decompose, and unfortunately, that releases generally H2S, which is hydrogen sulfides, which can get in our atmosphere and, of course, can choke other animals out. It's very dangerous. Marine algae can produce dimethyl sulfide, which is DMS, and that can affect clouds also. And another thing, of course, is when we burn this coal, there's different levels of coal and oil. Coal in particularly, if we burn kind of the cheaper one, if you will, what happens is it's loaded with sulfur, and that gets into the atmosphere, and of course, that can contribute to acid rain. The big example around here is, of course, before we had our Clean Air Acts, we used to, with our paper mills, emit huge amounts of sulfur dioxide into our atmosphere. That would get up into the jet stream, end up over Canada, and what would happen is we'd cause acid rain, and it would actually destroy a lot of their coniferous trees, which is a main source, aka lumbering, of income for the Canadian people, so they weren't too happy with us. But our new Clean Air Acts have really cleaned that up quite a bit. That is actually it for Chapter 4. It's a lot, the cycles obviously being the hardest part, but we'll take some time in class to review it.